All right, folks, we're continuing with our second talk. Can you try if it works? Yeah, perfect. Right.
Hi. Yeah, welcome to my talk about sensors. So we are going to move a level down from CSS and layout rendering, probably. Who of you has done anything with embedded systems or something like that? Quite a few. We'll see how much I can tell you, but yeah, let's go. I'm Klaus. I work as a technical evangelist at a company called CrateDB. Actually, until the day after tomorrow. Then I switch over to Microsoft, which is a fairly larger company, probably. Yeah. And yeah, I'm a software engineer. So my view of this, of this thing and that wire attached to it is fairly limited. So I had that during my studies, but after tinkering with Rust for about a year, I kind of went into, why not program something on that ARM device and get something going there. And especially since I'm sort of a curious person, I kind of like to re-implement stuff on, just to get to know it a bit better, which is, something that we shouldn't endorse a lot, I guess. But it's it's a nice way to kind of get into stuff, all kinds of stuff. So last year I set out and said like, yeah, let's build something really complicated, something like a thermometer, and like make it not as easy, and add a Raspberry Pi into the mix and add some something like a sensor. And this will be done in an afternoon. I want to do it with Rust, so yeah, I'm gonna look for a driver because there is Python drivers, and who wants to do that? Yeah, of course there was no driver for Rust, so I set out and said, yeah, let's do something quick and dirty, and since it's something GPIO, so I kind of, how hard can it be? So I changed my agenda to implementing a driver. I had a Raspberry Pi, I had my sensor, I know what base library I wanted to work with. I had a reference implementation in C++. I had a Python reference implementation. So I said, like, yeah, it's gonna work out, I guess. I found a data sheet, and the data sheet contained one test. So I'll be fine. It also, my scoping changed from an afternoon to probably a few weeks. And yeah, so it's all easy, right? So yeah, the first thing I learned is that GPIO is not everything, it's mostly interrupts and events and things like the buttons give you. That what I was actually looking for is something like SPI or I2C, both of which the Raspberry Pi supports. But these are two bus systems essentially, and I2C is more common, so especially since SPI needs a pin for every device you plug in. So yeah. So I looked closer at I2C. I2C is something called integrated circuit from 1982, and it has a phenomenal bandwidth of 400 kilobits a second. There's actually faster variants, but yeah, I assume that this is more of in the vicinity of that small thing here. And it uses 7-bit addresses, goes up to 10 bits, and this lets you connect about 1,000 devices, which I thought was enough. Yeah, they are also able to connect multiple Raspberry Pis on the same bus, and the devices come pre-addressed. So if you want to connect 2 of those sensors, you're out of luck unless you get a second bus going, which in this case needs a second Raspberry Pi. So yeah, that's an easy start. This is what I had to do and wanted to do. So this is essentially this device here. So the Raspberry Pi, which is Raspberry Pi 0, it has 1 wire for voltage. Okay, I don't know, I should hold it maybe in this direction a bit more since you have a picture. So one device, one wire basically gives the sensor power. And there's two other wires, one of which is the data wire, so SDA for data, and SCL for the clock. So kind of it knows when something is actually sent and not just random noise, for example. And of course, there's a grounding to complete the circuit. So this is this is fairly easy to find out what the pin layout is and connect the things that are named the same. So this is the sort of complexity I was dealing with there. And yeah, the base library to talk to these I2C devices is called I2C-dev, and it's on Crates.io. Easy to find. It already comes pre-implemented with two drivers, one accelerometer and one barometer, thermometer, but a different one. And it's not easy to reuse these things. So, but I was very excited. I kind of took it as a sort of an example to work with. And since I2C-dev gives me all the lower level communication and including a few examples, that was quite nice to start off with. So the result was that I created a crate called BMP085, which is technically a different device. I have it somewhere in here. Yeah, I think it's that one. So it's a bit larger than this one. So this is a BMP180. You can see what the version difference makes. But they use the same driver. So this driver works for both of those devices, and it gives you the temperature and air pressure of whatever it measures. So the essential part of how to implement this driver was how to get the data out. These sensors have registers, basically. These registers are addressed using a U8 address, so that's just a byte telling it where to do stuff, and doing stuff means either writing or reading. So in case of this BMP, this means you need to read calibration data from the sensor, save it somewhere. Then you write to a command register until it's like, I want to have temperature next. Then you wait. And then you read from the data register and get what you wanted. And then you factor in the calibration data, and then you're basically done. So let's take a look how easy that is. So that's not readable at all. So yeah, the layout of the project is fairly simple. There's one file. It has one dependency. So yeah, let's look at the lib file. So it's an Apache license, in case anyone's asking. This is the default address that it got assigned to from the manufacturer, I assume. And yeah, there's some Rust code that basically it makes it very simple to deal with a couple of things. In this case, it's the sampling mode. So to pressure that kind of determines how fast it should, how long you should actually wait between commanding and reading, and it also factors into the command. We will see that later, but enums are very nice to use in this space in general. As you can see, there's also more of that, of these enums, especially for registers. This is very handy. You can use some hex literals there in order to map the addressing space quite nicely. In C++, for example, that was just a gigantic amount of constant variables that wasn't defined the header file, which is it's hard to find sometimes, the stuff you're looking for. These are the calibration registers I was talking about earlier, and this is the actual thing that does something, the control register, and this is where something is, where you read data from the data register. Then there's also two commands that you put in, like read temperature or read pressure. Of course, since we're in that space, we also need to convert between big endian and little endian, which is always quite fun to find out what you actually have to use. But yeah, you'll figure it out. You have one test. So yeah, this is where the actual reading happens. So you read the raw temperature by, as I said, sending sending to the control register. So the device comes in. So you have an SM bus write byte data. So you write exactly 1 byte to this register, and you add this command. So it's like read this, read or get me some temperature. Then you wait. In this case, 5 milliseconds, which is exactly according to the specification, but it's a blocking thing. You have to put it in there. And then you read from the data register and you hopefully get something back. If you are quicker than those 5 milliseconds, you will get some garbage data, probably, or an overflow, because you're doing some extensive calculations done here, and some of them fail quite easily, especially bit shifting things. Yeah, and there's a lot of those things that are really peculiar to drivers, I guess, because there's a lot more coming from that. And I've copied most of that. I tried to look through what it actually means, but it's quite hard to understand what the actual thing does. Since also it's not helpful that they use the register names to describe the variables. And yeah, this is from the specification, and it's quite interesting. The test kind of tells you if you're right or wrong. And yeah, the same goes for the pressure. The pressure has something in here that it factors in the sampling, which is quite interesting. So you have basically put in a binary pattern, and you add the sampling, so it kind of knows how long it should read, or rather how accurate it should be. And you have to figure out on your side how long you should wait in order to get the right reading out of this. And then the register here is, for example, 3 bytes. The other one was 2 bytes. So this time you have 3 bytes, and I wasn't really sure how to put this in, so I used the U32, and then I used an integer, a 32-bit integer, because I wasn't sure if there's negative pressure that it can read. Yeah. Something. These are the sort of things that you deal with a lot. So the read temperature is quite easy here. This basically directly gives you back Celsius. The read pressure is a bit more complicated. So you read the temperature in order to obtain a coefficient that you only get when you're reading the temperature. So the temperature influences the pressure reading quite a lot. And then you have the coefficients you read from your calibration earlier. And then you do a bit more of more or less random calculations of stuff. That makes it quite easy to kind of. So I started off using U64s, and then I narrowed it down until it fails, sort of, and then and then you return Pascal in the end. So that's the secret sauce, I guess, in there. So this is the struct itself. So there's no I don't know, big secret here. This is reading the coefficients. So the new method really goes into and reads like a bunch of 10 or something coefficients from the device and returns it here. And then you save it, and then this is for the lifetime. So I guess if you probably change altitude a lot, so if you calibrate it at the bottom of a mountain and then go up, maybe this changes. So I didn't try that. So if anyone does that, please let me know. Submit a pull request on GitHub or something, because that would be interesting. What I used was from the I2C dev library. Since this guy already created a barometer and thermometer trait, I implemented those. So this I thought was a nice thing to integrate with. So this was a fairly simple thing to do here. and as I said, the coefficients. So just a massive amount of reading done here, and then save it. It's nothing special. And here is the test. No, actually, it's more tests than that, but it's, yeah. First of all, I had to implement a mock device. And for the mock device to kind of save data and return it properly in order to test, what I was calculating there, since I wasn't really sure how this works. Yeah, there's a lot of stuff going into the calibration, so I faked the calibration. And the calibration itself, and the writing, of course, so I basically saved it into a variable. But the writing itself, so the test that was from the specification was basically giving you a bunch of coefficient calibration values, and then an input value, and then what the output should be. And then you kind of iterate on that as long as needed until it worked. Which is probably not the way to do this properly, but this is currently the only thing that I have in order to improve that driver. I added a few tests on top of that, so I tried to come up with some crazy values, and in the end also have a random testing that just shoots in reading values, and then it should not crash, is the main goal here. So yeah, that was a quick run through how to implement this. So, but we can look at it in action. So I'm here connected via SSH onto this thing. So it only has a network with me, right? And in order to connect an I2C device to a Raspberry Pi, you need to load some kernel modules that probably come with Raspbian. They're probably already loaded. And then you have some tools in order to work with all of that I2C stuff from the get-go. So you can do I2C detect, and then you get the matrix of stuff that is connected there. And as we can see, 77 is connected, so the sensor is sort of detected and ready to go. Now, I created like a small project here, which yeah, is as small as you probably have guessed. So this is just it just has the sensor driver as a dependency, and I2C def in order to get out those traits to use the barometer and thermometer in that way. And when we look at the code itself, so this is all extern traits up there. We have some use statements, and here are the barometer and thermometer traits. And this is an import for getting the I2C device from the operating system into the code, essentially because the operating system or the kernel module for I2C maps it as a regular device. And then you have that I2C -1, and this is your bus. And you write binary data to that bus, and then stuff comes back, and it all comes together, essentially. Yeah, instantiation, and then just an infinite loop of printing and waiting for stuff. So I already built it because building on a Raspberry Pi takes a while. So in this case, it should not do anything. And we have to run the binary directory because we want to use sudo to get it run. So, and yeah, this is it. So it reads that it has 25 degrees Celsius in here, and we can warm it up maybe a bit. So yeah, and of course it crashes. Yeah, yeah, that gives you something to work on the weekend. Yeah, I think I touched it, but that's the sort of stuff you deal with when you have devices, and yeah, I can turn it on again, but I think it doesn't change much. Yeah, so let's go on to the pitfalls, right? So this happens, especially this multiply with overflow. As we can see, this probably wouldn't happen in Python as much, or maybe not at all, since it has very let's say flexible data structures there. And in C also they sometimes do like yeah, use this number pointer and then you do some magic on it, and in the end you say it's like a yeah, this is now basically a 16-bit signed integer, and yeah, and it all kind of works. It's not complaining as much. Rust complains a lot, which is probably good because it makes you figure out the boundaries of the whole thing. Then endianness, of course, I dealt a lot with that because it's both of these give you a number. The question is only what number, and can you know sometimes it doesn't really say, or it's not clear what they actually give you back, and maybe sometimes it changes because you can read two registers with each a byte, and then you have a 16-bit number, and you know you can use it however you want. It's maybe not right though. Yeah, the tests or test or however many you can make out is very interesting, and this was valuable feedback, right? It's not. I tried it. I have used this sensor and this driver a lot of times, and it never crashed for me like that. So I can use this valuable feedback to kind of try and figure out what went wrong there. And yeah, it's, you know, there's different, since this is physics a lot, this could be very different experience for someone who lives in Peru or something, where they have like 1,000 meters above sea level by default. And here we have like, what, 30? So there's differences in, yeah, in a lot of things, and it's very hard to get it right. And of course you have, you know, some minor things like cross compilation issues that, for example, these I/O things don't build very well on a Mac because there's something missing that I didn't know what it was. I just used a virtual machine because Linux works really well. And of course, dependencies, you walk straight into dependency hell if you don't keep it updated, or yeah, if you add too many dependencies and you have like, I think this driver has now like 4 just by adding one crate. But it, yeah, other projects I have like 100 dependencies just from nothing, essentially. Yeah, and of course I learned something. So the drivers are not that scary to implement. They're sort of fun, actually, and you can interact with the real world. And especially since I2C is fairly simple as a bus system to work. You know, it's like 2 operations and registers and addresses, and then you're good to go. But the devices itself make it sort of complex to work with, and that's also kind of the interesting part of all of that. Rust as a language works really well on low memory devices, and they have yeah, you can create something very nice with also very little effort, or rather little effort. I did something with TypeScript the other day, and it kind of, you know, it only took pictures of about 3 megabytes, then serialized the picture that took about 10 megabytes. The whole application had about 110 megabytes for some reason that I didn't know. And yeah, it used to run out of memory because the garbage collector didn't go in as quickly as I thought. So yeah, it was not as great as experiences with Rust, unfortunately. And yeah, there's a lot of CPU architectures available to build for, and it's, yeah, drivers are great to just do stuff with IoT. Then you can yeah, fancy yourself being an IoT person quite quickly. So yeah, as a summary, if you didn't pay attention until now, I have just grab I2C def. If you have an I2C sensor, figure out the messaging protocol, wrap it into a nice API, and find tests. It's I think the main things to do here. Something that's nice to work with is the Tessel, since it has comes prepackaged with Rust API for all of their sensors, I think. and it's a similar board as the Raspberry Pi, and yeah, has documentation and all kinds of stuff. And yeah, the other two things are the links to the crates I've been using and developing. So thank you. It's now time for questions, and you can follow me on Twitter, maybe.
Questions? Anyone wants to go first?
So maybe I wasn't paying attention when you showed the code, but did you use any unsafe features, or was it?
No, it's all safe.
It's all safe.
Yeah.
All right, that was it. Thanks.
It still crashed. Yeah. that doesn't make it any crash safe. Yeah.
Just one question. I saw you use it on Raspberry Pi. Did you try any barebone MCUs, like an ARM Cortex or something like that?
No, but I thought, so when I started, I thought of creating, like there's this Rust operating system project there is, that you also can run on a Raspberry Pi. I thought of using, trying to do that and make it just, only have a driver. But I think this would have went too far, so no.
Anyone? Anyone else? Okay, then I'm calling it. Thank you very much.
Thank you.
And thank you everyone for attending. It was really nice. And you can stay around if you want. I'm not going to leave immediately. So if you want to eat some of the leftover bagels or just have another drink and talk, you can do that. But you are also free to leave, of course. And yeah, see you next time. We will have a meetup in late October. I haven't settled on a date yet, but we will let you know soon. Thank you.